right, here we go. So lesson 48 is on finding roots of complex numbers and what we call the nth roots of unity. All right, so this is kind of a weird section, but it's kind of interesting. So it says if a plus bi is a complex number and n is a positive integer, then if you have some kind of equation like z to the n equals a plus bi, there are n different solutions in the complex plane with multiplicity. Julia, can you put her away, please? All right, so find the 6 solutions in the equation x to the 6 minus 1. So if we did this in Algebra 2, all right, there was a certain way that we did this problem. Okay, I don't know if you guys remember this. We did this problem. But basically, you break it into the difference two squares first. So it would have been x cubed plus 1 times x cubed minus 1. And then we would break it into the sum of 2 cubes and the difference of 2 cubes. You guys remember this? Do you remember your same opposite always positive? Can you handle that? So it's going to be x plus 1, x squared, multiply the 2 together, x, 1. So it's same, opposite, always positive. It spells out SOAP, so it's going to be negative and then plus here. And then the other one's going to be x minus 1, and it's going to be x squared plus x plus 1, like that. So we can see 2 of the solutions are x equals negative 1 and x equals 1. No big deal. Those are real numbers, very easy to find. But we know that every degree 6 equation, so if I have something that's x to the 6th, it will have 6 different solutions in the complex plane. Does that make sense? Like I'm going to have 6 different solutions, counting multiplicity. All right, so if I have this right here, I can't factor it. So how do I find the solutions to something like that? Quadratic formula. If you can't factor, you do quadratic formula, right? So we would have x equals negative b, so 1 plus or minus the square root of b squared, so 1 minus 4ac all over 2a. So we get 1 plus or minus, we have the square root of 1 minus 4, so square root of negative 3. So I write that as I root 3 over 2. So if I want to write it in that a plus bi form so I can see how I graph it, it's going to be 1/2 plus root 3 over 2i, but also 1/2 minus root 3 over 2i. Do you guys see how we got those solutions? Yeah, because it's plus or minus. Now if we want the other solutions, getting kind of messy here, to this part, right, same idea. We go through the same process. So we do negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get negative 1 plus or minus. It's still a negative 3 under the root. So it's going to be I root 3 all over 2. So it breaks into negative 1/2 plus root 3 over 2i and negative 1/2 minus root 3 over 2i. Okay, and those are our 6 solutions. So we have 1, we have negative 1, we have 1/2 plus root 3 over 2i, 1/2 minus root 3 over 2i, etc. Okay, do you guys see the 6 solutions? Yes. And what's really cool about this, and this is what a lot of math teachers, they don't do this, which I think is really weird. Like, this is like the easiest way to find these solutions. You draw a pretty picture. So if I drew a beautiful picture of these solutions in the complex number plane, here's where all of those solutions would be. So remember, I have the real axis and I have the imaginary axis. So here's 1, and here's negative 1. Those are the first ones, the real numbers. If I want 1/2 plus root 3 over 2, it's right here. And then negative 1/2 plus root 3 over 2 is right here. 1/2 minus root 3 over 2 is down here. And negative 1/2 minus root 3 over 2 is here. And what you end up getting, if you connect all of them, is a beautiful little hexagon. Isn't that crazy? And it actually works out to be a regular hexagon. All of those are going to end up being 60 degrees apart from each other. Okay, is that cool? You like that? That's how we're going to solve questions like this in just a little bit. So it says each solution above is called the 6th root of 1. So therefore, each solution of the equation is called the nth root of a plus bi. So in the real number system, so if I was in the real number system, if I had x to the 4th equals 16, how many real solutions would I have for that? I would just have 2. I'd have the number 2 and negative 2, right? Yeah, it's 2 solutions, so 2 and negative 2. But in the complex number solution, it actually has 4 solutions. All right, those 4 solutions are going to be 2, negative 2, 2i, and negative 2i. All right, and you can check that. If you had x to the fourth minus 16 equals 0, you would factor into x squared plus 4 and x squared minus 4. Do you guys see where the plus or minus 2i is coming from? From the x squared plus 4. Do you guys remember that from Algebra 2? All right, so it says for each positive integer n, the non-zero complex number, a plus bi, has exactly n distinct, n roots, I don't know why I said that, n distinct roots. Okay, so these are given by, oh man, I didn't write this down. I'm going to have to think about it. I don't ever write it this way. Okay, I'm going to pause and I'm going to look at your book because I do a shortcut and I'll show you.